A cell is an enclosed environment, and that cell has to exchange materials with its surroundings pretty much constantly. Since the plasma membrane is the outer covering of the cell, the plasma membrane is going to be responsible for that exchange. Now, oftentimes, membranes are called semi-permeable. That term semi-permeable describes some of what the cell does. Now, it does allow some substances to cross and prohibits others from crossing, but really a much better term to use is selectively permeable. By selectively permeable, we're indicating better what the cell is doing. It's actually choosing what's going to cross that membrane. And that choice is going to be different from day to day or moment to moment, depending on the current situation of the cell. So we do want to keep in mind that membranes are able to choose the molecules that get to cross or do not get to cross the membrane. Now, when we talked about membrane structure, we talked about the fact that that interior of the phospholipid bilayer is going to be hydrophobic. That hydrophobic interior is really only going to allow hydrophobic substances to cross through. So if you do have molecules that are hydrophobic and they're relatively small, those are going to cross through that phospholipid bilayer quite easily on their own. For those molecules, we really won't be able to prohibit them from crossing the membrane. Everything else, though, things that are not hydrophobic and that are not small, they're going to need some help getting across the membrane. And that's what a lot of those inserted proteins are going to be responsible for. So for the help across the membrane, we're going to have specialized proteins which will be called transport proteins. Now, there are two different types of transport proteins. The first type is what we call a channel protein. And this first picture is showing us the channel protein. Since we already have an interior of the membrane that is hydrophobic, we don't need a hydrophobic passageway across the membrane. Instead, we need a hydrophilic tunnel or a hydrophilic channel. What this provides is a passageway that's something that is tiny and polar or charged is going to be able to cross through. Now, these channel proteins don't allow unrestricted access from one side of the membrane to the other. They very often can have gates on them or kind of doors on them, and these can open and shut different times depending on the needs of the cell. The other type of transport protein is going to be what we call a carrier protein, and the second picture is indicating the carrier protein. As the name implies, a carrier protein is going to hold on to molecules and actually carry them across. Now, this will actually bind to a molecule, so there will be a binding site, and when it binds to that molecule, it's going to change shape in some way, which is going to transport that molecule to the other side. Now, this one is going to be more specific than the channel proteins. With the channel proteins, it's primarily a size exclusion and just the fact that it needs to be something that is charged or polar that's passing through. If we're talking about the carrier proteins, since these are actually binding to a molecule, there's going to be a small, limited number of molecules that will actually fit that particular binding site. So these generally work on just one or a few molecules. All membranes are going to have some assortment of channel proteins and carrier proteins as well, and these will vary a lot depending on the molecules that need to cross across that membrane. We also don't want to forget that although we've somewhat focused on the plasma membranes in this chapter, there are other membranes in the cell, and these principles apply to those other membranes as well. So if we're talking about a membrane around the endoplasmic reticulum or around a particular vacuole, that will also have channel proteins and carrier proteins there. Now that we know some of the proteins that will help molecules get across the membrane, we want to just talk about molecule movement in general. Now, the first type of transport, or the first category of transport that we're going to cover, is what we would call passive transport. And passive transport across a membrane is characterized by the fact that it does not require energy. So for this, it really is not going to be any trouble on the part of the cell, okay, because it's not going to require an expenditure of energy, and they can just kind of sit back and let this type of transport happen. Diffusion is a type of passive transport. With diffusion, this is just the tendency for molecules of any substance to want to spread out evenly and take up all the available space. For example, if I had a container that had some fragrant substance in it, if I simply set it on the counter and it was still as can be, if I removed the top to that container, those molecules would start to exit and spread out. And this means that very quickly I would smell them, then the person next to me would smell them, then people even further away would smell them. And all of this is because those molecules are spreading out on their own, and they want to take up now all of the space available in the room, since now they have more space available to them. Notice that I didn't have to shake those molecules around. I didn't have to turn the container upside down. They will spread out if I simply remove the lid and now give them more space. Now this applies to any molecule. So all molecules want to spread out and take up the space that's available. When they do this, each molecule is going to move randomly, but the population of molecules is going to move what we call directionally. So if we look at an example of this, here we see a picture where we've got molecules spreading out. Now notice that they're fairly concentrated together. These molecules are bouncing around all over the place, and they have an entire slide here which they could take up if they wanted to. So they're going to slowly spread out and take up the space available on this slide. Some of them actually bounce back towards the center, more concentrated area here, and some of them bounce the other direction. So we're saying each molecule is moving randomly. As they do this, though, the population is spreading towards the corners of the slide. So we're saying that the population is moving randomly, the population is moving directionally, but each molecule on its own is moving randomly. Now, when these molecules do actually end up spreading out and taking up this entire slide, do you think that they will stop moving? Each molecule is going to continue to move even when this entire slide is taken up and is occupied. However, at that point, although they will still be moving, the population is not going to be moving directionally anymore. In other words, we're going to have a nice even concentration pretty much over this entire slide that we're looking at. So if we look at this diagram here, we've got a bunch of molecules on this side of the membrane. Here they're pretty crowded. They're basically at a high concentration, and they would like to have more room. So if we have a membrane that has holes in it or pores in it that these molecules can actually squeeze through, this is then going to provide them with more area that they can move in. So notice that at this point then, the molecules are going to want to move to this other side, which has a very low or no concentration of them. So we're going to see them move from what we would say is a high concentration to a low concentration. Now, as the molecules start to move across, they are moving directionally. This means that some will actually be moving right back towards the highly concentrated area, while others are moving towards the lowly concentrated area. They will continue to do this until we get to what we call equilibrium. Now, equilibrium is when we basically have even concentrations on both sides of the membrane. In other words, we are as spread out as we can possibly be at this point. However, notice that the molecules are still moving in the diagram. So we're not going to stop movement just because we've got equal concentrations on the two sides. Now, diffusion applies to any molecule or any substance. So any substance wants to diffuse down what we call its concentration gradient. And by down the concentration gradient, we're saying that those molecules want to go from high to low, or from a region where they are highly concentrated to a region that they are lowly concentrated. We saw that already for the orange molecules. If we add a second molecule here, now we have a purple molecule. This doesn't change anything about what the orange molecules are going to do, because the orange molecules are going to move down their concentration gradient, and the purple molecules will move down their concentration gradient. So for the purple molecules, if we look at them, on this side they are high, and on this side they are low. And we said that any molecule wants to go down, or from high to low. So for the purple, they're actually going to move in the opposite direction. So they will move down their own concentration gradient, do their own thing, while the orange ones are moving down their concentration gradient. All of this will continue until we get to equilibrium. So until we get an even concentration of purple molecules on both sides of the membrane and an equal concentration of the orange molecules on both sides of the membrane. Now this principle of diffusion we said applies to any molecule, so it certainly applies to water as well. And this is where osmosis comes into play. Osmosis is probably something that you've heard of before in the past, and osmosis is a type of diffusion. So osmosis is specifically diffusion of water, but not only is it diffusion of water, but it's diffusion of water across a semi-permeable membrane. So this means that the water will cross the membrane, it will be permeable to water, but there will be solutes that cannot cross. Okay, so we're going to be looking at diffusion of water. Keep in mind that when we're talking about cells, we're certainly talking about aqueous solutions. So solutions where water is the solvent and you've got lots of solutes, ions, sugars, things inside the water. And we will be evaluating the water's concentration gradient, and this will be very much affected by solutes that happen to be dissolved in the water. So if we draw a picture here, okay, on this slide I've got a semi-permeable membrane. So by semi-permeable, some stuff can cross, other things cannot. I've got two different solutions here. On one side I'm going to have a lot of solute, and on the other side not as much. Now these are aqueous solutions. So this means that these molecules are going to be dissolved in water. Now if you review how water actually dissolves things or acts as a solvent, it does so by making a hydration sphere or a hydration shell around these. So on this side here where I have all this solute, I've got a lot of water that happens to be bound to the surface of the solute, and I've also got some water that's floating around. On the other side I also have solute, albeit a different concentration of solute, a lot less. On this side, because I do have less solute, I actually have more water that's floating around that is not bound to the solute. When we're talking about diffusion, or osmosis, it's diffusion of free water. And what we mean by free water is that it's going to be unbound water that will be moving across this semi-permeable membrane. So since it is the diffusion of the free water, we need to evaluate the free water concentrations. So on this side, I have a high concentration of free water. There's certainly more than what I have on this side. So this side has low free water. And with osmosis, it's a kind of diffusion, so it's going to be high to low. So the water molecules are actually going to move towards the region that has the higher solute. Notice this side has high solute, and this side over here has lower solute in comparison. Now it's important that we understand that this is a semi-permeable membrane, and by semi-permeable membrane the water can cross but the solute cannot. Because if the solute could cross the membrane, the solute would be moving down its concentration gradient. Okay, so the solute is not going to be crossing the membrane. It will be stuck for whatever reason. It's too big or it doesn't fit the properties to cross the membrane. And we evaluate the free water concentration. Notice that the higher the solute, the lower the free water that you have. So you have an inverse relationship between the amount of solute and the amount of free water. If we look at this picture here, this is just an image from your textbook that shows this principle of osmosis. In the middle we have a semi-permeable membrane. We've got a close-up shot of it down here. This semi-permeable membrane is not going to allow these green molecules to get across, and these are sugar molecules. So they're stuck on whatever side they happen to be. Notice that on the outside surface of these sugar molecules, we have water molecules bound. So we're making a hydration shell, which is why these are actually soluble in our water. Notice that on this side, we have high solute, and if we have high solute, we have lower free water. On the other side, we have low solute, and this is going to mean that we have higher free water. And remember that it is our water that's moving. So the water is going to go from high to low. So it will move in that direction. It's going to continue to move in that direction until we get to equilibrium. When we get to equilibrium, then the population will stop moving directionally. Doesn't mean the molecules stop moving, but the population stops moving. Notice that in this case, basically, we end up at equilibrium when we have equal sucrose or sugar concentrations on the two sides of this tubing that we have right here. Now, the reason that this is important to us is because this affects cells in solution. So if we go back to this picture, keep in mind that if we apply this to a cell, all we have to do is take one of these membranes and circularize it. So now, rather than talking about the right versus the left side of the slide and which way the water wants to move, we can talk about the inside of the cell versus outside of the cell. Now this is going to be what we call tonicity. So tonicity is the ability of a solution to cause a cell to gain or lose water. Now, while this applies to all cells, this is going to have an even greater impact on cells that do not have cell walls. And our good example of a cell without a cell wall is going to be an animal cell / a human cell. So it'll have an even greater impact on these compared to, say, plant cells. Now, as we saw before, what determined which way the water wanted to move was the free water concentration. But what affects the free water concentration will be the concentration of solutes in that solution. And not just any solute, but these are going to be the non-penetrable solutes. So in other words, the solutes that cannot themselves move through the membrane. Keep in mind that if they could move through the membrane, they would be diffusing down their own concentration gradient. So we have different types of tonicities for solutions. And if you do know your prefixes, that helps a lot as you go through these different solutions. Now, the names of the solutions always apply to the amount of solutes in the solution. So if we look at this first one, we have an isotonic solution. And iso means same. So what this is saying is that you have the same concentration of solutes outside the cell as you have inside the cell. And if you have the same concentration of solutes in both compartments, you have the same concentrations of free water in both compartments. And this means that although there is some water moving back and forth, we're not having a directional movement of that water. For an animal cell, this is going to be normal. Okay, so this is the ideal situation for an animal cell to be in. To not be gaining water, to not be losing water. Now the next type of solution we want to talk about is what we call a hypotonic solution. And a hypotonic solution, hypo means low. So we're basically saying that we've got a low solute concentration, and keep in mind that solute concentration is inversely proportional to the free water concentration. So if you have a low solute concentration, you have a high free water concentration. In contrast, inside the cell, you happen to have a high solute concentration in comparison, which is going to mean a low free water concentration. And water moves from high to low. So since the water is moving from a high free water concentration to a low free water concentration, we see the water actually enter the cell. So the water is moving across the membrane and to the inside. Now we have to keep in mind when the water is going to stop moving inside the cell. So when does equilibrium occur? Equilibrium occurs when we reach equal concentrations of free water on both sides. What this means is that if there is just a small difference in concentration on the two sides of the membrane, maybe only a little bit of water needs to enter the cell. And the cell membrane is kind of stretchy, so it can stretch and accommodate some extra water. However, if the concentrations are too different on the two sides of the membrane, then it would take a lot of water moving into the cell to actually get to that equilibrium point. And the cell membrane can only stretch so much without bursting. So if you do have too much water enter the cell, we're going to end up with what we call a lysed cell, which is a burst cell. So if we have a burst cell or a lysed cell, that is a dead cell. So this is a deadly situation for a cell that does not have a cell wall to actually be in. At the other end of the spectrum, we have the hypertonic solution. Hyper means high, so if you think hyperactive, and this high is referring again to the solute concentration in the solution. So we have a high solute concentration, and that means we have a low free water concentration in comparison to inside the cell. So again, water moves high to low down its concentration gradient. In this case, it means that the water is actually going to move out of the cell. So we're actually dehydrating or removing water from the cell, and we end up with a shriveled cell. Again, it's really related to how different those concentrations are, because water will continue to move out until we get to equilibrium or until we don't have any more water that's available to move out. So this is a shriveled cell. This, depending on the severity of it, can also be a dead cell as well. Now, a good example of this is when we talk about salt water. So you've probably heard before that even if you are dehydrated, you should not drink salt water because that will just make the problem worse. Well, the reason for that is because if we're talking about salt water is obviously very salty. Okay, so that salt is a solute in the water. And since there is so much salt there in the water, it's going to be a very high solute concentration, and that's going to severely lower the free water concentration. And this free water concentration is going to be much lower than the free water concentration that you have inside your cells. So if you take a dehydrated person and they consume salt water, they're basically bathing their cells in a hypertonic solution, similar to what we see in this picture. This means that any water that you did have in your cells is going to start to leave your cells. So you're not helping the situation, you're actually making it even worse by drawing the water out of your cells in a faster fashion than what had occurred before. Now, that's our cells that have basically a plasma membrane with no cell wall outside of them. Now, if we're talking about plant cells, remember that plant cells have cell walls. Many bacterial cells also have cell walls, so this isn't strictly limited to plants. But the cell walls are going to change things up a little bit when we talk about tonicity, because the cell walls help to maintain water balance. If we talk about these same solutions in regards to a plant cell, first off, we can look at the isotonic solution. The names of the solutions don't really mean anything different. In the isotonic solution, we still have the same concentration of solutes in both compartments, so water is entering and leaving the cell at an equal rate. And for a plant cell, this is not ideal. This is what we would call a flaccid cell, which is going to be a pretty flimsy cell. This would be a plant that is not particularly healthy, it's somewhat wilted. Now, if we look at the hypotonic situation, in a hypotonic solution, we have high free water outside, and inside we have low free water. And we said that the water is always going to move from high to low, so we see it actually go into this particular cell. Now, when we didn't have a cell wall there, we had to worry about the cell actually gaining too much water and bursting or lysing. That's never going to happen in the case of a plant cell. This cell wall is a rigid box, very supportive, that is around the outside of the cell. So it's not going to stretch too much. So it will stretch a little bit. You can see the bowing out of the cell wall a little bit in this picture. But once we really have packed as much water as we can inside that box, no more will fit. So we're never going to rupture that plasma membrane. This is what we call a turgid cell. And for a plant, this is an ideal situation. So this is going to be a plant that has nice crisp leaves, upright in stature, perfect situation for a plant cell. If we look at the other end of the spectrum where we have the hypertonic solution, the hypertonic solution, you've got a lower solute concentration inside the cell, which is going to mean high free water inside the cell. The water wants to move out. Now, if we have a lot of water move out of a plant cell, we risk what's called plasmolysis, or getting a plasmolyzed cell. With a plasmolyzed cell, we actually have a separation of the plasma membrane from the cell wall. So we end up with air spaces within the cell. This is lethal to a plant cell. Where you might see this take place is if we're talking about watering a plant with salt water, for example. Some other kind of common examples that you might be familiar with if you do some cooking is if you ever salt cucumbers. When they talk about salting cucumbers, you take cucumbers and you apply salt to the outside. That salt draws the water out of the cucumbers so that they don't have as much water content inside of them. Another situation would be if you bake a lot of fruit pies, if you're using fresh fruit. So if, for example, you cut up apples and you have these apples and you mix in a lot of sugar and spices with them, you stir it up in your bowl, and then before you know it, what was a dry mixture now has a bunch of water in the bottom of the bowl, or liquid in the bottom of the bowl. That is because when you apply all of that sugar and spice to the outside of the apples, you're creating a high solute concentration outside with very low free water. And the water that is inside the cells wants to leave the cells, and it begins to move out and creates that liquid environment. Now here we're just seeing a microscope picture of some petal cells. So these have a purple pigment throughout them. We see that we have turgid cells over here. So these turgid cells are filled with a nice even amount of purple pigment. And then the other side is showing you the effects of salt water. So if you were to surround these cells with salt water, it's going to cause the water to move out of the cells. And this means that that membrane is going to shrink. We're getting plasmolysis. So these white areas are representing the air spaces that we have within those cells. So these would be dead cells at this particular point. You want to make sure that you do review the three different solutions, hypotonic, isotonic, and hypertonic. And we want to know what that means as far as the direction of water movement. So is the water going to want to move in, move out, or do we have equilibrium? We also want to know how this affects an animal cell versus a plant cell in these three different environments. And another aspect, if you have a picture of a cell and you see some concentrations of solutes in the two compartments, we want to know which direction is the water going to be moving, or also be able to use those tonicity terms. All right, so we've talked about diffusion, and osmosis was just one type of diffusion. Now, facilitated diffusion is along the same lines, but now we're going to involve some channel proteins and some carrier proteins. So in this case, we're now going to have transport proteins that speed up the movement of molecules across a plasma membrane. So keep in mind, if we have a membrane here, that membrane has a phospholipid bilayer. And we said that this phospholipid bilayer has a bunch of fatty acid tails inside, which create a hydrophobic environment. So this is hydrophobic, And the only things that really want to move through that hydrophobic core would be other hydrophobic molecules. So if we had this other molecule out here, a very high concentration, and suppose this had a charge on it, if we have a high concentration out there and a low concentration on the inside, the molecules would want to move across that membrane. They would want to move down their concentration gradient. However, they're going to have a very hard time actually doing that because they can't get through that hydrophobic core. Now, given enough time, they will move through the hydrophobic core one by one, just as we said that occasionally we can get a flip-flop in the phospholipids from one side of the bilayer to the other side. But that could take a very long time. So if this is a molecule that we would actually want to move across that membrane, we're going to use our carrier proteins and our channel proteins to help it across. So if we first look at the example of the channel proteins helping with facilitated diffusion, we already said that the channel proteins provide a hydrophilic corridor or hydrophilic tunnel that runs from one side to the other. Well, in this picture, we can see that we've got high concentration on the top and a low concentration on the bottom, and the molecules want to go high to low. So all we're doing here is we're basically providing a passageway that they can now flow through to get from one side of the membrane to the other. So if we simply open that door, they will start to flow through. Notice in this case that we're not making anything happen that wouldn't normally happen. Those molecules want to go high to low, and they will go high to low. They simply would take a very long time to move high to low if they didn't have that little tunnel there. So by adding the channel protein, we are speeding up this process of diffusion. And that's what we mean by facilitated diffusion. We can also use carrier proteins to do the same thing. In this one, we still have a high concentration of molecules on the outside and a low concentration on the inside here, and they want to move high to low. We simply provide a way for them to get across that membrane. So we're binding them on the high side, we're releasing them on the low side. So here we've had a few examples of passive transport. When we're talking about passive transport, several things we want to keep in mind. So we already said with passive transport that there's no energy required. And that is true. There is absolutely no energy required for passive transport. Notice that in all cases of passive transport, we move from high to low. So in other words, we're moving down a concentration gradient. When this happens, we may or may not use a transport protein. Okay, when we saw regular diffusion, that did not use a transport protein. When we used osmosis, that did not use a transport protein. But if we start talking about facilitated diffusion, we could use either carrier proteins or channel proteins in that case. Okay, now in contrast to passive transport, we also have what we call active transport. Active transport is essentially just the opposite. So with active transport, notice that now we're going to require energy. This is because we're going to be moving substances against, we could also say up, their concentration gradient. And what we mean by up or against the concentration gradient is that now we're going to go from low to high. This is like rolling a ball up a hill. It's not going to be easy to roll a ball up a hill, so to make that happen, we would actually have to put some energy in to make it happen. So while we're requiring energy, this energy is usually going to be in the form of ATP. ATP is adenosine triphosphate. That is a molecule that we'll talk about quite a lot in chapter 8, 9, and 10. And this is a short-term energy storage molecule for the cell. So when you see ATP being used, at this point we should just be thinking that that is a small amount of energy that's being utilized to run that particular process. Now if we look at this picture, we can see that on this side of the membrane we have a low amount of molecule, and on this side we have a high amount of molecule. So the molecules would really like to go high to low. We talked about that. But if these have a charge to them, they're not going to move across that phospholipid bilayer very easily. If this is a very good molecule for the cell, it's beneficial to the cell to spend some energy and actually accumulate it inside. So we're going to have a carrier protein involved here. That carrier protein is going to pick the molecules up from the low side and it's going to transport them to the high side that we see. As long as we have energy available, we're able to move these molecules up their concentration gradient, or from a from a low concentration to a high concentration. We cannot use channel proteins here. Now the problem with the channel proteins is going to be that if we simply open a tunnel, the molecules are going to want to flow in the other direction. So if we open up a tunnel, they're going to flow high to low, which is exactly what we don't want to happen here. So we really are limited to the carrier proteins in this case. Now this slide here just compares the passive transport versus the active transport. With passive, we're always going high to low, no matter what. When we're going active transport, we're always going low to high. Passive, no energy. When we're talking about active, requires energy. Active also requires help. So it requires a protein. Specifically, it's going to require a carrier protein. And then if we're talking the passive transport, we may or may not have a carrier protein there, just depending on whether we're talking about diffusion versus facilitated diffusion.